And now, after so much waiting, we have here the binomial distribution. We will see what is it. This consists of the type of experiment, the random variable, and what is the probability function. Then we will see why it is like that. Then we will see how its mean and variant are, or how mean and variant it is. And last one, we will see its relationship with the snake, with Python. On IVA! So, the type of experiment we will have and what is its random variable. The experiment consists of many trials. We have trial 1, trial 2, trial n. Each trial have two outcomes, either winning or losing. And the probability for each event of winning have to be the same number, which we will call p. Another thing we ask is that all these trials must be independent. The random variable we want from this experiment is the one that gives us the number of winnings from an event. And this can be achieved as setting y equal to small y's, where every y is 1 if we win in the first, second, third, and so on trial. So yi is equal to 1 if we win in the trial I, on 0 if not. So in the end, y, the sum of the little y's, counts the winning. Let's see an example. Playing the lottery 5 times is one of these examples. If we only buy one ticket each time we play, then we have n trials, which is playing the first time, the second time, and so on. In each trial we can win or we can lose, and the probability of winning and losing are the same because we bought the same amount of tickets, which is 1. Also, each trial is independent. Another example is if we buy the same amount of ticket each time, then the probability remains constant. It is still a binomial experiment. What is not an example is if we buy different tickets each time we play the lottery. Then the probability changes in one trial or the next one, and then it's not a binomial distribution. Another counterexample for this is, let's say we have a bowl with different white balls in it and one red ball, and we pick 5 little balls. The trials will be picking one ball. Each experiment has 2 outcomes. Either we have a red one or a white one. We win if we have red, and we lose if we have white. Each trial is not independent, and therefore is not a binomial distribution. Why they are not independent? Because if we pick red on the first trial, on the other trials it's impossible to get red. Now we have to see a really important part, which is the probability function. What is the probability of having k success? And it's given by this formula here. Now, why is it like that? So the probability of winning the first k event and losing the rest is equal to power k times 1 minus p power n minus k. So probability of winning k times first and then of losing the rest of the times. But we are interested of all the different possible ways we can win k times, not only winning on the first and then losing the rest. So how many ways we have here of having k success? By what we saw in another video, this formula here coincides with how to put n elements into 2 boxes, one of capacity k and the other one with capacity n minus k. The first box will be the success box and the second box is the losing box. And the elements are not elements but the trials. Now let's see the mean and variance of this. So the random variable y was the sum of little y's. Each of these little y's are independent from each other. Moreover, we can calculate the expected value or the mean of each of these elements. The 0 times the probability of being 0, so losing, and 1 times the probability of being 1, so winning. And that gives us p. Now we can calculate the variance using the formula we saw in a different video, and that gives us p minus p squared, which is equal to p times 1 minus p. Then, using the linearity of the mean, we get that the mean of y is equal to the sum of the little means. Each little means is exactly equal to p, so it's equal to n times p. Now, because each y is independent from each other, will be the sum of all the little variants, and in each of these little variants is equal to p times 1 minus p. So the full thing is n times p, 1 minus p. Maybe you want a screenshot for this. Now we will see the relationship with the snake. Imagine this circumstance. We are wizards in a magical world, and we go with a party into a dungeon. We have the instant KO spell that we can use only 3 times per battle. We go into our adventure and we get into 25 battles. We record each time our spell works. We have this, the first time we go into battle, it works once. The second time, it works 2 times. We could kill 2 monsters. The third time, it didn't work at all, and so on. After we finish our adventure, we come back into our headquarters. We want to predict what will happen next time we go into an adventure. We think this could work as a binomial distribution because each time we go into a battle, we can use 3 times the spell, and the result will be it works or it doesn't work. The probability seems to be the same each time we use it and to be independent each time we use it too. We decided to speak with the serpents in our headquarters. We calculate the mean of the data we have and the variance of the data we have. If it is a binomial distribution, then the p we have should be the expected value divided by the amount of trials in each battle, which is 3. Let's see which numbers we have. So let's see what the snake said. P should be equal to 0.3, more or less. Your directed variance should be 0.63, blah, blah, blah. And the variance we have from our data is this one here. So the theoretic data, if we say it is a binomial distribution, it is very similar to this one here. So something else that snakes can do is that they can produce, using the binomial distribution, some database. So how do we do that? Here is the spell for the snakes to produce a size 25 data from a binomial distribution given that the number of trials is 3 and the probability is 0.3. We need to transform this database into float in order for the expected values and the variance to be more accurate. We also ask them to compute the expected value and the variance of the database they are creating and compare it with the P and V, the real P and V from which the database is created. Let's run it. So we get these numbers. The P varied a lot from the real P, and the variance varied a lot from the real variance, even though we are sure that this data is created from a binomial distribution. Our real data looks suspiciously well. It has better numbers than this one, and we are sure that this one works with the binomial. We are not so sure about this one working from the binomials, but it gives us better numbers. What we can say about this is that there is a high probability that our spell works as a binomial distribution. So we can try to predict what is going to happen next time and then actualize our data and do all of this again until we have a big data and then be sure how our spell works. Hope you enjoyed this. See you later, Pythonator.